All right. Welcome everyone to the next New York Combinatorics seminar. Today we've got John Cutler, who's going to talk about anti-Ramsey numbers.
Thanks everyone for coming, and thanks to the organizers for inviting me. So today the goal is to give you an introduction to some problems that are related to anti-Ramsey numbers, but it's getting close to the end of the semester, so this is meant to be a gentle talk. So please interrupt at all times if anything's unclear, especially if you think I'm making a mistake, because I probably am making a mistake. So let's start off with the definition. Generalized number. And I'm not sure, we probably haven't settled on the best notation quite yet, but for now, something like AR for anti-Ramsey, G and H are graphs, Q is a positive integer. The maximum number of colors that can be used color the edges, oops, not of Kn, but of G. So G is our host graph. We're coloring the edges of our host graph, so that every copy of H sees less than or equal to few colors. Okay, so G is your large graph you're coloring, and H is your sort of smaller graph, and you put a cap on the number of colors that each copy of H sees. Okay, so there's no reason for you to understand that quite yet. So we're going to talk about what that means, and we're going to take our time. We're going to do Deepak's trick of thinking about what upper and lower bounds on this number mean. Okay, so and even I'm going to use my notes because this is the kind of stuff that I'm going to make mistakes at. So so first note, that's right. So if we have an upper bound, so what does it mean to prove an upper bound on this generalized anti-Ramsey number? It means that every coloring of E or G, and I should point out that when I say K coloring, I mean that I'm using all of the colors. Okay, so I could introduce another word for that, but I'm going to define what I mean. I'm just telling you that I'm using all the colors there. Contains, oops, copy. So this is too many colors, right? And so we've exceeded this number. So it contains a copy of H with at least Q plus 1. Right. Let's see. Right. So that's what an upper bound means, right? So we've exceeded this maximum, right? And what is a lower bound? How do we go about? When we think about a lower bound, that's a construction, right? So that means that there exists a K colony of G in which every copy of these. That's the Q grows. Right. So this is the proof side. This is the construction side. Is that okay with everyone? Okay. Okay, so let me give you some, so I've called it the generalized anti-Ramsey numbers. So let's think about why this is related to the classical anti-Ramsey numbers. So here's another note. And if Zoom people can yell at me when they can stop. I know I can go to about here, but when you can stop reading it, let me know, please. So the classical anti-Ramsey number has to do with Q equal to E of H minus 1. So this is classical anti-Ramsey number. Introduced by Carriage. Shows in 1973, I think. Yeah. And so what are you saying here? You're saying that every copy, you're coloring the edges of G so that every copy of H sees at most the number of edges in H minus 1 colors. What does that really mean? It means that there's no rainbow copy of H, right? So this is, yeah. I use TMC for totally multicolored. Is that okay with everyone? So totally multicolored copy. Okay. So so this in this paper they did some they introduced the anti-Ramsey number. They use different notation for this, of course, but I'm going to use our notation because I don't want to introduce too many more functions. And one of the big things they did was they made a conjecture which said that, well, they were interested in their host graph being the complete graph, and for the vast majority of this talk, our host graph was going to be the complete graph. And then they were interested in finding cycles, and of course, since they were interested in the anti-Ramsey number, then they wanted since the number of edges in the cycle is k, and they wanted to see at most k minus 1 colors, each copy of ck. And they made a conjecture that this was some constant dependent on k times n. The constant is k minus 2 over 2 plus 1 over k minus 1 plus little r1. And I know I'm getting close to going off the board for Zoom, but and this constant came out of construction. I'll show you a version of that construction in just a second, as a simple case of that construction. Yeah, but this was their and they actually proved the case. So they proved. And I think a good warm up for us today is to go through that proof. Okay, so what is this? This is talking about triangles. You don't want to have any totally multicolored triangles. And you're asking for the maximum number of colors you can use to color the edges of the complete graph. Is it okay so far? Okay. So
yeah. If you could explain that totally multicolored.
yeah, so sometimes it's called a rainbow colored. So it means that every edge in your copy of H would have a different color, right? And so in this case, if you're like in the case that we're about to do with where C is equal to 3 and you're talking about C3s, you're trying to avoid triangles where every edge is colored a different color. Okay. All right. So since we've written them in this order, let's do the bounds in this order. So let me first prove to you. So let me first prove that FAR of n C3 2 is strictly less than n. Okay, and so what did they do? They came up with this nice idea which said, well, let's imagine, so let's color E of kn with n colors.
So your goal is exactly n, not a little low.
I think it's going to be n minus 1. Our goal is n minus 1. I mean, so they have an off.
A little low.
They have an off by a constant, so we're gonna prove actually. So we'll prove that FAR of kn C3 2 is equal to n minus 1. All right, so let's color it with n colors, and then we're going to take what's called a representation of this coloring. Okay, so take representation of this coloring. So what does that mean? That means just take one edge of every color, right? So one edge Color. So what do you get? You get a graph that's totally multicolored that has n edges, right? And what do we know about graphs on n edges? That graphs with n edges on n vertices, they definitely contain a cycle, right? So since I mean they called it Gn, so we can call it Gn. So so since u of Gn is equal to n, Gn contains I don't know what length, but it contains some cycle, right? And so let's look at that cycle, right? So here's what that cycle looks like. Sorry, I'm not going to use multiple colors because I'm too tired. And would be way too slow. So here's my totally multicolored cycle. Let's imagine that it has, oh, not
Yeah.
okay, that, yeah,
Or
yeah, no, I don't care. So some number of vertices in it, right? What I'm going to show you is I can chomp down and get a triangle, a totally multicolored triangle. So these are all different colors. So consider this edge here, right? This edge is colored some color. And that the color, whatever color this, if this is color C, then C can either show up on this side of the cycle or it can show up on this side of the cycle, right? So take the side of the cycle where C does not show up. And then what have I found? I found a shorter cycle. And then just
or the case that could be a different color.
Mhm.
If you already have your,
yeah, sorry.
if it's a new color,
Yeah.
you got your triangle, otherwise.
Yeah. So yeah, exactly. So it can show up in at most one side, right, of or at least at most one of the paths from V1 to V3 on the cycle. And so therefore take whatever side, the side that it doesn't show up at the end, and you shorten the cycle so you can just continue to do that until you get a triangle, TMC triangle. So that one pause. Right? So n is too much, right? So how do we show that n minus 1 is enough? We need a construction, right? And so here's the construction. Just order your vertices of Kn in any way, and then color them by their left-hand endpoint. Color the edges by their left-hand endpoint. So all of these edges are going to get color 1. All of these edges are going to get color 2. All of these edges are going to get color 3 and 4. And this one edge is going to get color n minus 1, right? And then if you take, in fact, any cycle in this graph can't possibly be totally multicolored because you need to return at some point to where you started, and that's going to have an edge with the same. There's going to be at least one edge, 2 edges that share a color, right? And so therefore, n minus 1 colors is we've found an example of a coloring of the edges of Kn with n minus 1 colors that does not contain a TMC C3, right? So this tells us that FA on of well, now C3 2 is minus. At least see, I know I was gonna mess up. Is that right? Yes. So that does the job for this. Is it okay with everybody? So okay, so good. All right, so that is that's the classical anti-Ramsey number, right? So you might wonder, like, what about people have been interested in this generalized anti-Ramsey number before, and the answer is yes. Oh, I should say, the conjecture, before I go on, the conjecture has been proved.
By you.
Proved Alon, I'm not going to get the dates right here. So 83. He proved the K equal to 4 case. I think it was his PhD dissertation, actually, or at least part of it. And then by Ballesteros and Norman Rara in 03. Right, so the conjecture has been completely proved. Okay, so 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 now, so that's. So now you might be wondering again, about the generalized anti-Ramsey number. It has been studied before, sort of rather sporadically. So the most studied version of the generalized anti-Ramsey number is when both your host graph and your smaller graph are both complete, right? So this is. Okay, so if you think about this construction again, going back to this construction, okay, this construction gives you a bound actually for this in a very particular case, right? Because if you have a complete graph on p vertices, how many colors is that going to see? It's going to see p minus 1 colors, right? So because it will see all the colors except for the largest vertex of the vertices, right? And so well, actually, so note the earlier construction that F A R A N A P. So each copy of KP sees at most P minus 1 colors. And how many colors did we use total? We used N minus 1 colors. So it gives a lower bound on that. And in fact, that's been proved to be a quality. So a theorem of oops, that's a high. Bang. Again, the years are the things that are going to elude me. In 92, they proved that F A R A exactly this is equality rather than inequality. And then I'm going to be a little bit wishy-washy about about the second result. So I'm going to write it down carefully, but I'll kind of explain what I want to see out of it. So this, in this case, KP has P choose 2 edges, right? And this is much less than the total number of edges that they graph. So this is quadratic and P, the number of edges in here is quadratic, this is linear. If you are interested in sort of getting closer to a quadratic number of edges, which is getting closer to the actual anti-Ramsey number, then they had another result, which is FAR and AP TPK plus Q prime. Okay, so what is this? This is the Turon number. So this is the number of edges in the Turon graph with P vertices total and K parts in it, right? So this is a complete K-partite graph where each part is as equally sized as possible. Okay, and this is equal to Tn. Okay, so this is again a Turon number, U prime. So think of this as being sort of, I mean, very, very roughly speaking, this is about 1 minus 1 over K times P squared, right? And this thing is roughly 1 minus 1 over K times squared. Okay, and so you're talking about sort of, this is getting some sort of, this is near a quadratic number of edges in your number of colors in your KPs, and you're getting near to a quadratic. I mean, this is quadratic number of edges in your for your bound, right? And they have a rather exact thing. And there's some actually restrictions, so I'll write it down. So it's here, and 1 less than or equal to Q less than or equal to some crazy number like P over K, roughly half the size of the potatoes.
You mean Q prime?
Sorry, yeah, thank you. Yeah, thank you. That's very good. Thank you. Yeah. Okay. So all I want, the takeaway message here is somehow like this is where the number of colors is linear. This is about where the number of colors is quadratic. And you get quadratic. Okay, so then in a follow-up paper, Eksonovich and Kungden refined these two results. So, this is just one case, right? And you might wonder, where do I get sort of linear or maybe sublinear bounds? And that's what, so here's a theorem. One of it. And O1, they said that so this is bounded by a constant times n, provided that Q is at most p minus 1. So if the number of colors you want to have show up on in each copy of KP is less than or equal to p minus 1, the right-hand endpoint of this interval is exactly the result of Schroeder and Kai and Zhang, sorry, then you get an upper bound of linear on it. And they had another result, which is hard to read. I'm going to write it down. And again, I'm going to give you a wishy-washy hand-waving version of my take on it. So they have some technical condition on this number k. So if k is the minimum of the k primes, such that the Turon number of p with k prime parts in it is at least q. If that whole thing is less than p, then this part is not actually that important. This is the important bit. So then what do you get? You get that the generalized anti-Ramsey number Kn Kp Q is the Turon number again. So this is k mod of 1 plus some smaller error thing. So if k is decent size, then this is quadratic, right? And this is some quadratic term. So what is this saying basically? So let's just think about the transition between, so if this is k is a minimum, right? And what you're doing, q is the fixed number of colors you want to have show up, right? And so as k is increasing, what are you doing? You're taking a Turon graph on p vertices and you're splitting it into more and more potatoes. And as you split into more and more potatoes, the number of edges is going up, right? And this is the number of edges, right? So initially, right, when k prime is 1, you have no edges. And as soon as you get to k prime is 2, you shoot up to something around n squared over 4 edges. So you shoot up to quadratic, right? But if k prime is 2, right, then this is giving you a sub-quadratic bound, right? So this is then 0, right? So the key bit is like this transitions between, so if k is 2, then you're getting something like the FAR is sub-quadratic, right? And if k is 3, then FAR is actually quadratic. That's what I care about. So this transition, okay? And so these are the kinds of questions that actually we were interested in doing, except we were interested in doing them in a different case. Does that make sense? So linear sort of realm or sublinear realm, or like this isn't really sublinear realm. It's the realm where you're at most linear, and then this is some transition between subquadratic and quadratic. Okay. Cool.
Could you explain?
Yes, I mean, I don't actually want to dwell on this because the version of that I'm going to do is much simpler. I just wanted to give you some sort of history and show you that these things were things that people were thinking about. So basically what you're doing is saying as Q increases somehow, and I'm going to talk about this in detail in just a second, Q increases, then you're allowing for more and more colors in your host graph. And what we're going to be interested in is when the number of the sort of transitions between constant and linear, when it hops from constant to linear, and when it hops from maybe linear to quadratic. Those are interesting spots. Okay. Okay. So yeah. Those two things would have been good to have on slides, and then I could have gone through them relatively quickly. Yeah. So now I promise to calm down, to settle down now a little bit. So let me just point out, but I do want to give credit where credit was due. So of course, so here's sort of some toy questions. So what if, again, KN is going to be my host graph, okay, until you start thinking about the problem, and then you can think about different host graphs. So if I think about a silly question like this, then any guesses? Yeah, so you want the maximum number of colors so that every copy of G sees at most one color, right? And as long as your graph has at least two edges in it, right, then this is going to be what, right? You're not going to be able to use multiple colors. So if G, I think, right? So unless you're in this kind of silly case where you don't have enough edges to see anything. Okay, so if you start with a small number of colors, you are definitely small, right? Your anti-Ramsey is very small. And at the other extreme, oops. So here's the other extreme. So what are you doing here? You're trying to color the edges of Kn so that every copy of G sees at most E of G colors, right? But this is no restriction, right? Because you can't see more than the number of edges of colors, right? So you might as well just color all these edges different colors, right? So this pops up and chooses, right? Okay. So what's happening here is that sort of as Q goes from 1 to E of G, right? Then you're constant for maybe a while. I don't know, maybe not very long. I have no idea. And then at some point, so you're constant in here. Ish, I'll say constant. Maybe I'll say even sublinear.
Yeah.
Right. So you're sublinear for a while, and then you hop to something that's superlinear, superlinear subquadratic. Right, so I don't know exactly what those things are, but maybe you're something like a constant times n, right? And then at the end, you're quadratic. And the questions we were thinking about were, when does this happen? So when do you go from sublinear to linear, right? Or superlinear, and then when you go from subquadratic to super quadratic, or just quadratic. I can't say super quadratic because quadratic is bad. Is it okay with everyone? So this is going to be called this is what we're going to be calling the linear threshold. This is what we're going to be calling quadratic. And what we initially tried to do is we initially tried it with paths, and then we realized that we were thinking about worked for trees, and then we realized that everything we did worked for connected graphs. So we were trying to make the problem easier on ourselves, and then we realized that it works.
Just to get clear,
Yeah.
in between when it's like end of the A where A is between 1 and 2.
That's right. That's right. So, and I don't know, I don't know exactly what those things are. So, and maybe it's linear for a while, and then it goes super linear, and but I'm trying to be very here, right? So, what I'm thinking of, there's a constant regime, basically, and then I'm gonna think there's a linear regime.
So it depends on spanning trees.
It depends so it depends on something. I mean, in some sense, it depends on a spanning tree, but it also just depends. So it depends on max degree, and then it also depends on your matching number. So what is the size of your larger matcher's matching? That's what this depends on. And this one depends on something a little bit funnier. So yeah. Okay, so let's think about the linear threshold. So I think in the abstract, I said it for trees, but I can do it for the same proof works for connected. Okay, so let's do the easy stuff first. Let's do the construction. Okay, so in fact, there's going to be two constructions and we're going to use both of them. Okay, so here's two constructions. So here's this will give us a lower bound, right? well, yeah, let me not say that. It's a little confusing with the threshold. So constructions. Okay, so here's one construction, which is called the star coloring. Okay, so what am I going to do? Well, it's exactly what you might think you should do. I'm going to take one vertex. Well, let me actually draw this slightly differently. Sorry. I'm going to take one vertex. I'm going to color all of its incident edges different colors. So 1, 2, 3, and -1, right? And then I'm going to color everything else with an nth color. Okay. So I've used n colors total to color all the edges of Kn, right? So if I embed a graph G in there, then what's the maximum number of colors it can see? Well, it depends on which vertex I sort of map to this vertex, right? And the most and the number of colors I'm going to see is the degree of that vertex plus 1, perhaps, right? So what does this tell us? I mean, so what's the kind of worst case scenario, to use a bad phrase of all beginning graph theory students, is to put the vertex of max degree here, right? And so I think I get something like this builds that FAR of AN G delta of G plus 1. So every copy of G is going to see at most delta plus 1 colors. And how many colors did I use? I used N. Makes sense? So as soon as I get, so that means that, and there's nothing about G here really at all, right? Except that it has max degree G. So what have I gotten? As soon as I reach this many colors, right? I turn the dial for the number of colors that I'm linear for sure, right? Okay, so I've already hit linear at that point. Okay. So what's another thing I can do? We don't have a big, or I don't know, for this. I shouldn't blame you on. So I don't know, that matching coloring.
Oh yeah.
Yeah, do we have a name for that one?
I thought it was said Toronto.
Oh, that's much fancier. Yeah. Okay, so what do? We take as big a matching as we possibly can, right? So, and we use different colors on the edges of that matching. I don't know why there's so many edges. So this is floor of n over 2 eventually, right? And then we use one more color, so one additional color on the rest. And so what does this give us? So this means that whenever I embed my graph G, oops, G, then I have to embed the edges that are going to get different colors in the matching are going to have to form a matching in G as well. And so what's the most colors I can pick up? The matching number of the graph. And so we use nu of G plus 1. Plus 1 is because the one additional color, right? And so that is at least, right? Again, linear, right? So as we're turning up the number of colors, right? As soon as we go past either of those things, either delta plus 1 or nu plus 1, then we have reached the linear regime. Does that make sense? Okay. So if we let K equal the min of the max degree and the matching number of our graph, then what we've done is shown that FAR of AN G A plus 1 is at least, or I guess I should say equal.
Mhm.
It's at least linear, right? So as soon as I hit k plus one, I'm linear. Does that make sense? Where k is the minimum of the max degree and the two. Okay, so the question is this the actual transition spot, right? And it turns out that it is. So so further. F A R K N G K is equal to, or maybe I should say less than something like. I think we do k plus 2 times k plus 1 actually. Deepak, so, so something like this. Okay. So this is constant in n, right?
That other thing is.
So this is omega of n. So it's
The one above that.
this one. This is the matching number of G. Yeah. So it's the size of the largest matching in your graph. Okay. So this is linear in n, right? Sorry, not sublinear. This is constant. Sorry, constant in n. It's the end of the semester. Sorry. I think my brain is already on Thanksgiving break next week. So yeah. Is it okay with everyone? So I'm not gonna do all the details of this proof because the details are a little bit gross, but I'm gonna at least give you the idea and like the key tool for us to prove this. And I'll probably do a pretty bad job of describing how it goes. But Deepak's here, so you can help me if I make too much of a mess of it. So, okay. So again, what do we want to do? We want to take an edge coloring of Kn with this many colors, right? So, edge. And then we're going to take a representation, right? So again, right? So representation again is a one edge of every color, right? So the number of edges in all. Gonna use your other white one.
Yeah.
Okay. So then it turns out a very nice result. So what would we like to do? We'd like to find a large star or a large matching in R, right? That's the idea, because if we can do that, then that will show up. There'll be some copy of G that we can map either the large matching or the large degree vertex into that, right? So it turns out by a result of, let's see if I can get this right, Abbott and Sauer, 1972. If your graph has at least this many edges, we know that R between either a star with just two edges or a matching. With K2 plus 2 edges. And which is lovely. So I didn't know about this result before this. Yeah, and nothing about just number of edges. That's so you do contain a large star or a large matching.
Sorry, so
yep.
if you have a graph with
Yep.
that many edges,
Yep.
then you have that.
And you have one of those two things. Yeah. The result actually is a bit better than what I've written here. It's they have actually sharper results for, I think this is the right number if k is even. And if it's odd, they could do a bit better actually, so, but we just need.
And there's also like asymmetric thing, like if you want a star of size A and a matching of size B, then it's
Yeah.
8 times B-ish.
Yeah,
Yeah.
it's a very helpful thing,
It
so,
makes sense.
I have a question about your, you improved it.
Yeah.
Did you pick these two kinds of colorings before this result, or see the result and pick these two kinds of colorings?
we doodled for a long time with trees first, and then, and like with small, like, I think we first started off with paths and we were. And like we realized matching
Yeah.
was somehow the right thing to do, and then we thought about stars, I think.
Star coloring came up in
It
like
was
the
the-
Erdish paper,
yeah,
like
yeah.
that's somewhere.
Yeah. or
And
maybe
then you
not
hunted
the
down the
newspaper.
times, and then you're like, oh, there's the trade-off between star and matching. You found
Yeah, I mean, it took us a while to get there. I
Yeah,
guess,
yeah, okay, yeah.
But eventually we realized there was some balancing between
Yeah.
having a large degree vertex and having a large matching, and somehow these were the right things. I mean, I think we did basically a bunch of cases with different trees first. We saw where things kicked,
Right.
and then basically where it was able to interpolate. the
And
work.
there are some other results in the history that we didn't talk about, but like Tao Zhang
Yeah,
has
yeah,
a lot of results
about stars.
about
Yeah,
stars.
Yeah, yeah.
And anti-Ramsey of stars, and basically the generalized anti-Ramsey of stars,
We did,
they
yeah,
end up
yeah.
being like kind of, for stars, doing the general version versus doing the whole thing is kind of like, it doesn't matter or something, you know, and so he has results, and then we were looking at those and seeing some stuff, so
Yeah.
it popped out of that.
So basically, so, you know. This is too many colors, right? So we've got an excess of colors that we want to find inside of a copy of G. We want to find a copy of G with k+1 colors, right? And so what we basically do is some finagling, and this is where I'm going to be a little hand wavy and wishy-washy. What we do is basically we say, well, G is either small, whatever that means. So it's basically got something around. Oh, and I'm just going to do this case. So let's assume that this is true, that that R has a star. So G is either small, meaning it has around delta +1 vertices, and then there's some small cases to deal with, or it has a like subdivided star, okay, or I think this is sometimes called a broom, where there are k-1 edges here and then one additional edge here. So you can find somewhere in your graph something like this, and then you just play the game with this star in the representation, and something similar to what Erdős did with the cycle. You say like, okay, well, let's consider edges between leaves of the star, or like off of the leaves of the star, and you can find that's total multicolored of those, then you can embed this version into that totally multicolored version. So I mean, extremely hand wavy here, but hopefully that's, and then you do a similar thing with a matching. You find some sort of somehow like a matching, and then maybe something like this, or maybe a slightly longer, and it goes through in that case the same way. So that gives you essentially no idea about how the proof goes, but it gives you some idea of what we were looking for. Does it make some sort of sense? Hopefully, there's some fiddling here. But it's not hard fiddling. Yeah, cool. I don't have an enormous amount of time left, so maybe so that like aside from that hand waving there, that gives you an idea of for connected graphs where this thing happens.
If all you care about is linear threshold, could you replace that k by k+1 and have the proof be easier?
Except if I go to k+1, then I'm
okay,
super linear, right? So this is saying that the transition actually happens between k and k+1, right? So yeah, cool. I mean, this proof is a little fiddly, but it's not too hard. It's not too fiddly. It's not like 20 cases. It's like 5 cases. So yeah. So cool. So let's do the larger threshold. Let me just give you an idea of where the larger threshold happens and maybe why it works out the way that it does. So what about quadratic threshold? So it turns out that if you have any graph, so here we can sort of adapt some results of Mumbai and West from, again, the date is everything happened around the same year. So that sort of relate FAR to extreme numbers. Okay. So, and even Erdős Szymanowicz and Schoch had made this some sort of connection here, but the ones specifically that we're using are due to Mumbai and West. So it turns out that how do I want to do this? I think I just want to do one version, like one direction of this, basically. So just to give you a flavor of what these things, how this goes. So G is any graph, and M is the number of edges in the largest bipartite subgraph. E. Then, oops. So of course, if G itself is bipartite, then that's just the number of edges in G, right? So then if you go one below that, then you're subquadratic. Okay. And it turns out that like the transition for bipartite and non-bipartite happens at different places. So of course, if you're bipartite, then the transition is going to happen at M there because you can go to N choose 2. If you're not bipartite, the transition happens one step later. So and that takes a little bit of extra work. But let me show you that this is true. Basically follows from Erdős-Stone. So let me, I guess this is a plane. So so let H be that bipartite subgraph. With is. And then what are we going to do? Let's consider a coloring of E of Kn with the extremal number on N and H's plus 1 colors, right? This is the maximum number of colors in an N vertex graph that contains no copy of H. So if we exceed that by 1, then we're guaranteed to have a copy of H, right? And so, so then any representation contains a copy of H. And as soon as we have a copy of H, then we can just plop in the rest of G wherever we in an immutable way, which implies it's a copy. Sorry, a TMC copy of H, right? Which means a copy of G. C at least. Is that right, M?
Yeah.
Yeah, and so therefore we get that Kn G M minus 1 is at most one less than that, right? The one less than the color that we use, and Irish. That gives us, since H is bipartite, that gives us little bit squared. Cool. Yeah, and you can use extremal numbers to get upper bounds as well. There's a little bit more work you need to do, but that's the job. So cool. That's what I wanted to cover. I just wanted to tell you that basically everything's open beyond what I told you. So we don't know anything about like the fine details. So we know where we go linear and we know where we go quadratic, but like, are there regimes where you're sub-quadratic? Sub-quadratic superlinear. And then the other one that I mentioned is that like other host graphs are essentially the Wild West, other than K and N. So other host graphs. So not KN. Except K and N was done. Is that Mumbai and West again? Is that right?
Yeah, they
Yeah.
did something with
Yeah.
that.
So in that same paper that I mentioned here, Mumbai and West looked into K and N as a host graph, but like there's all sorts of other host graphs you can random hypercube, all sorts of other cool stuff that you can think about. Cool. All right. Well, thank you.
All right, any questions on Zoom or in person? Not in person.
Is it easy for the host graph thing like PN?
It might be easier, but it's not something we've thought about.
So
So
it's not like one of the,
yeah, I mean, like, so you can only think of
say, path subgraphs, like, or like path pieces
Yeah.
or something.
yeah.
Wait, what are you saying?
I was thinking
The
like
host
host
graph
graphs
is
is path.
Path.
Yeah,
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 that I
yeah.
think that you can do that.
You can, yeah.
But like actually
It splits it up. Yeah, I think you with not too much thought, you could do that.
Right.
Yeah.
But like even binary tree might be interesting.
Yeah, I mean,
Yeah.
actually what got me into this was thinking of tree hosts and path target.
Okay.
So arbitrary tree hosts
Right.
and the path target. I think that's what I was thinking about. And actually maybe even a vertex version.
Oh, yeah. Oh, sorry.
Something
yeah.
like that. So like, yeah, you could call it a vertice.
Yeah.
So I saw some paper about that and I was like, this sounds like Ramsey or generalized Ramsey. Oh wait, it's generalized anti-Ramsey. Oh wait, you know, and then it kind of like led me.
Yeah, and there's a whole other literature of the dual problem here, which is the Ramsey version of all these things, where everything gets turned on its head. So, yeah.
So I think you mentioned the threshold is connected. Is
The-
that different? Is
Yeah,
that not connected?
I think, yeah. So in the proof, so the constructions still work if they're not connected.
Yes.
But the proof needs connectivity in order to find this broom-like structure. And so, yeah, I don't know what goes on if you've got multiple components actually in here. Yeah, I don't know. It's a good question.
I'll just make a comment that like it actually the fact that when it transitions from sublinear to linear, it's constant that entire time and then goes straight to linear. That's very different than the generalized Ramsey problem, where it hops up through all these polynomial values until it just kind of gets to linear. You know, it's like you have things like square root of n and the 5, 6, and you get all these intermediate polynomial values, and then it hits linear eventually. This one's constant, and then goes straight up. So that's kind of a strange
Yeah.
behavior.
And also it'd be kind of like another thing we were thinking about when we were thinking about trees, like, can we actually think about for like even that constant regime, can we get some idea of what those constants are? Like, or like, when you get to linear, can you think about what the coefficient of it is? So, those are other, good, like I said, tons and tons of questions floating around it.
So we don't have a definite interval where we know it's linear or we know it's quadratic, it's like, we have the points where we don't have that.
So for this for this problem, we know that the whole, until we get to K, we're constant.
We're constant,
Yeah,
and
so,
then
but then once we hit
It's just
linear, yeah, we don't know what, we know it jumps to linear. And we don't know what happens between there and the quadratic.
And it's probably related to values of bipartite extremal numbers, which are hard. Do you know what I mean? Like, doing the extremal numbers of bipartite graphs and getting those fractional exponents. It's probably related to that, and it's as hard as that. It might just be equivalent to it.
From Zoom.
Yep.
Yeah, Jonathan, very nice presentation. I just thinking about notation. I saw that in the literature. It doesn't seem to have particularly standardized.
No.
But my suggestion is that since we usually use capital R for Ramsey, a backwards capital R seems like pretty natural for anti-Ramsey.
Yeah, that's good. Yeah, I like that.
It's available on typesets because it's a letter in the Cyrillic alphabet.
Awesome,
Oh, cool.
awesome. That would be good. Yeah. I know
Just a thought.
Yeah, no, that's a very good. I like that suggestion, actually. I know that other people have used little r and big R to distinguish the cases, which I didn't like very much.
Yeah, that's a little too common. Yeah.
But the
I've
backward,
seen a lot of little AR, big AR,
yeah.
FAR, a few used.
Backwards are.
But I do like backwards R. You may get,
Yeah.
If the paper, if our paper gets published in the next, or written up even in the next 5 years, then.
Takes up less space. You got to say that for it. Yeah. Anyway, nice results. I like the what you're going for here, which is the asymptotic behavior. It makes a lot of sense.
Right. Cool. Thanks very much. Yeah.
Other questions? All right, let's thank John again. All right.
Thanks, everybody.
The